This video is about digital oscilloscopes. It corresponds to section 15.2 of Applied Analog Electronics. Now, I'm not going to talk about all different kinds of digital oscilloscopes. There's just too many of them. I'm just going to talk about the general idea of digital oscilloscopes and the particular one that we're going to use, which is the Analog Discovery 2. Now, this particular type of oscilloscope, sometimes referred to as a USB oscilloscope, because it's hooked up to a computer with a USB cable. And this division of the oscilloscope into two parts, a front end that deals with the analog and with the timing, sampling, sort of all the analog interfacing stuff, is put in this little box, and all the controls and displays are done by the computer. This splitting the work into two different things is very good for making a low-priced instrument, because I don't have to put displays, which are fairly expensive devices. I don't have to put knobs, switches, and all that sort of stuff. All I have to put in here is the essence of the oscilloscope, which is the amplification and the sampling, the analog to digital conversion for that. Now, this particular device actually has a lot more capabilities than just an oscilloscope. It's also a dual power supply and two arbitrary waveform generators. Now, you may be noticing that there's this huge bundle of wires out here, and the oscilloscopes we looked at before had a couple of oscilloscope probes, and that was it. Well, it turns out that if you really want to use this thing like a conventional oscilloscope, you can buy a board that you would plug in place of all those wires, same connector, that provides BNC connectors here for hooking up your oscilloscope probe. And if you do that, then you can have some of the advantages of the oscilloscope probes, which is, say, you can go to higher frequencies, and you can have higher impedance on the probes if you switch to the times 10 probe. Now, the trouble with that is your voltage also gets switched down by a factor of 10, and that means you lose some of the resolution here. You need higher voltages in order for the Analog Discovery to see it, because the amplification in the Analog Discovery 2 is limited to a particular value, and if you stick a voltage divider in front of that shrinks your voltage by a factor of 10, then you're going to need 10 times as much voltage to get the same signal visible. For what we're doing, which is mainly low frequency signals, these wires are perfectly adequate. We do not need to have the extra expense of the oscilloscope probes. Alright, which of these wires do we use? There's still way more wires here than we need for an oscilloscope. That's because half of these are used for a digital logic analyzer, for studying digital logic. Since we're not doing that in this course, we don't use that functionality. We use a lot of the other functionality, though. We've got a pair of orange wires here, the first things on the left, and those are channel 1 of the oscilloscope. The solid orange wire is the positive, and the white stripe is the negative. And you always need to hook up both of these, because this oscilloscope is a differential input. It's always looking at the difference between these two signals. And that means they both have to be connected. If you don't have a differential signal to look at, you're looking at something that's referenced with respect to ground, well, just hook your negative input up to ground. But always hook it up to something. We've also got a pair of blue wires, a blue and white. And these are exactly the same sort of concept, but they're for channel 2. And we've got a red wire and a black wire. You may remember my saying that in this class, red wire is always the positive power supply, black is always ground. Guess what? The red is the positive power supply, and the black wire is ground. You can go up to 5 volts on this power supply. There's another wire, a white wire. That's a negative power supply. And again, it's with respect to ground. And it can go down to -5 volts. And finally, the other two wires we use are the yellow and the yellow and white. That's not a differential pair. Those are two totally separate function generators. The solid yellow one is waveform generator 1. The yellow and white one is waveform generator 2. And I believe you've already used waveform generator 1 in the sampling and aliasing lab. We're not going to do that today, though. We're just going to look at the oscilloscope. And in fact, I'm only going to look at channel 1 of the oscilloscope. Now, these fly wires here have got, if we point that at the camera, not behind my head, you can see there's little square holes in the ends of those black plastic things. These are female headers. Those square holes, the only thing that should ever go in them are male headers. You do not want to stick wires directly into a female header. The reason is that copper wires are fairly fragile and they can break. And if you break off a wire inside the female header, you may not be able to get it out again. And that would mean having to cut the wire, crimp on a new female header, which is not that easy a task, and shorten the wires in any case, so just don't do it. Always use male headers. And that's why when we're making connections to a board, we use double-headed pins. Let's see if I can get that actually on the screen here. The double-headed pins, one end goes down into the breadboard and the other end sticks up, and we can stick a female header on that sticking up pin. Alright, so let's in fact do that. Let's hook up some of these wires. Now currently I've got everything turned off, and so I can hook up this without having to worry about, oh, I'm putting on too large a voltage or something like that, because the power supplies are turned off, oscilloscope's turned off. I can just hook things up. So red wire, that's 5 volts, that goes to the positive input of the board. Oh, I need a black wire for ground. That goes the other end here to the negative input of the board. I want channel 1, the orange wire, to go to the output of the board. And I want the negative input of channel 1 to go to ground. I have to hook it up to something, and since I've only got a single-ended output here, ground is the sensible thing to hook it up to. Okay, so that's it. I have now hooked up channel 1 to the output of my hysteresis oscillator. You'll be building one of those later this quarter. And I've hooked up power and ground to it, but I haven't turned on the power supply yet. So let's go over to the software. This is waveforms. It is in the state it's in when you just start it up. Behind me is the serial number for the particular Analog Discovery 2 that I have, indicating that it's found it. What do I want to do? Well, over here is a whole bunch of different things that I can do with the software. And for this demo, I just want to look at the power supply and the oscilloscope. Let's start with the power supply. All right, we've got two supplies, the positive supply and the negative supply. They're both ready, which means neither one is currently running. I will turn that one off. It's not even ready now. If I turn on the power supply, it's not going to turn on, just the positive one will. And I don't want it to be 1 volt, let's make it 5 volts. Okay, so now when I turn this thing on, it's going to be a 5 volt power supply. Two places I can turn it on. One is this master enable button. Now it's on, now it's off. And that's handy when I've got this big panel in front of me, but most of the time I'm not going to have the power supply panel in front of me. I'm going to be looking at the oscilloscope or one of the other tools. So there's another little button up here next to supplies that, when it's a triangle, that says, it's like a play button. It says, hey, if you click this thing, it'll turn it on. And then there's a stop button that says, hey, if you click this thing, it'll turn it off. And I can do that even when I don't have the power supply panel in front of me. So let's turn on the oscilloscope. But my choices over here disappeared when I hit the power supply button. So there's a little plus sign here that gives me a drop-down menu, pop-up menu actually, I guess, that lets me pick the oscilloscope. So this is what the oscilloscope starts out looking like. And it's not currently running. And now the power supply, let's turn on the power supply with a little button up here. I can turn on the scope the same way, or again, there's an internal button, run here. And it produces this picture. It doesn't look very good, because I was expecting an oscillator that oscillated between 0 and 5 volts. I didn't expect a constant line down here. I didn't expect what looks like noise here. But if we think about this a little bit, it actually starts to make a bit more sense, because this blue line down here, that's channel 2. I didn't hook up channel 2. Let's just go over here to channel 2 and say, turn that off. Okay, that's gotten rid of one piece of junk. Then there's this sort of orange thing here. It's looking like noise. What might be the problem there? Well, I am looking at 1 millisecond per division. You can see 0, 1, 2, 3, 1 millisecond per division. But what was my oscillator designed for? Well, I didn't remember what I designed this one for, but I suspect I designed it for a much higher frequency. So maybe I did it for 1 or 2 megahertz. So let's look at it at a higher sampling rate. So instead of 1 millisecond per division, let's try looking at 1 microsecond per division. Now it's looking like it's going between 0 and something off the top of the screen. That's looking much more like it might be the square wave we want. Okay, but it's going off the top of the screen. I want to see the whole thing. What can I do? Well, I can change the vertical scaling. I can say instead of 500 millivolts per division, I can say let's look at that at 1 volt per division. And now I can sort of see the top there. It's just at the edge of the screen, but this whole thing's up too high. I'm not using 2 channels here. I don't need channel 1 at the top, channel 2 at the bottom. Let's use more of the whole screen. And there's 2 ways that I can drag this thing around. One is this arrow way over here at the left. I can just click on that and drag it. And now I've dropped the 0 there. And now I can see that I'm going between 0 and 5 volts. And incidentally, sometimes the yellow on white is a little hard to see. You can go to this gear icon over here and change the color. And sometimes I like to do sort of a dark red. Sometimes you can go black if I'm trying to do something that's really easy to see. Okay, so there I have my signal. And I can see that it is a square wave. It's going between 0 and 5 volts, and there's a bit of ringing at the top and at the bottom. And that ringing probably is real. It's probably a result of trying to use those fly wires rather than a proper oscilloscope probe. It adds some extra inductance, which gives some overshoot in the ends here. But this is, notice, this is running at just a little less than a megahertz. And that's already pushing what the fly wires can do. We're not often going to be running at these frequencies. Okay, so I can see my signal here. What else might I want to do with it? Well, this black triangle at the top here is telling me when I trigger. And notice that unlike the analog oscilloscope, where the trigger was always, that's what starts the sweep, so it's always here at the left edge, here I can put it in the middle. I can see what happened before the trigger. And that's one of the really big strengths of a digital oscilloscope, is I can look back in time. Because what's happening is that it's continuously making measurements, doing analog to digital conversion, and storing those results in memory. When it gets the trigger, what it can do is just say, okay, I'll run for a little while longer to record what's happening after the trigger, and then freeze what's in memory. And I can have left stuff in memory that happened before the trigger. I can also move this trigger around. I can say, well, oops, get this in the right window here. I can say, let's move that back to here. Now I'm looking at just 1 microsecond before the trigger and 9 microseconds after. Or I can drag that over to here and say, let's look 9 microseconds before the trigger and 1 microsecond after. It's also visible here on the position. The position is saying what's in the middle of the screen. And I can move that position back a moderate ways, so I can look back in time up to sort of the amount of memory that it is willing to save. And I can go quite a ways in the other direction. I could say, hey, when you get the trigger event, wait a minute and then give me the results. Record what happens a minute after the trigger. So I can have a positive value here that's quite large. Negative, it's limited by how much memory I've got, how much capture before the trigger is observed. And it's still a handy thing to have. Be able to see, hey, I've got something that's going wrong. If I can set up a trigger that says, hey, trigger when the thing goes wrong, then I can look at what happened just before things went wrong. Maybe that'll help tell me why things went wrong. So it's very useful for debugging to be able to look back to what happened before the trigger. And you can only do that on a digital scope. There's a lot of control of the triggering up here. So you notice the trigger here is sort of down here, something that's happening near 0 volts. Well, what it's saying is that channel 1 is rising through 0 volts. That's the triggering event. Now, 0 volts is not a very good thing to pick because there's a lot of noise on the bottom here. So we could make that level be something different. We could make it be, say, 2 volts. And now notice that this vertical rise here is right in the middle. And actually, something I'm not showing you because it's behind my head, a little triangle right here. That's the trigger level. I can move that around to say, you know, I want to trigger right at the beginning of this thing, but I don't want to get that ringing noise, so let's put it about here. And now I'm triggering at 700 millivolts. And again, you can see it's a nice, clean rise right at the trigger. Maybe that'd be easier to see if I put the trigger back in center. And again, I can move it by moving this arrow, or I can do it just by typing the number here. Okay, there's a lot more that this oscilloscope can do, and you're probably going to need to read some of the help documentation for it. One thing that's particularly useful for this class is the measurements panel. Because what I can do here is I can say, you know, what I'm really interested in is what's the frequency of this thing? Or maybe perhaps what's the period? So I can say, I want to add a measurement. Hit this plus sign here, I want a defined measurement. And what I don't want channel 2, I want channel 1. And is this a vertical property that is to say something about the voltage, or is it a horizontal property, something about the time? Well, it was frequency or period, so that's a horizontal property. And there's frequency. I can say, add that. I am now reporting what the frequency is. Or I can say, well, maybe I wanted the period. I can add that. And they're now being reported here. And as you can see, things are fluctuating a lot, and so it's flickering around quite a bit. I can do other fancy things here, but one of the simplest things to do is just to stop the thing from running and look at what's the current value. That's 815 kilohertz or 1.2 microseconds. Okay, that's great. I said that this board was a touch sensor, and I had a touch plate on there. What happens if I touch that touch plate? Well, the frequency goes way down, the period goes way up. In fact, it's gotten so big I can't see it on the screen here. I don't have a full period on the screen. So what I can do is I can say, well, let's change that so we're looking at maybe 50 microseconds per division. Now I can't really see what's going on there. And this weird gray stuff at the top, that's saying there's something going on here, but it's not really easy to see what's going on. So what I can do is in channel 1, if I hit the gear icon, I can say, don't show me where there's noise. And that just shows me sort of the clean signal without sort of that noise band around it. That's a result of it's estimating measurement noise. Okay, so frequency here is very high. I can't really see it. It's looking like solid black. But if I touch the touch panel, now I'm taking it down to about 33 kilohertz. So that's an enormous change in frequency. And you can see it's still fluctuating, and that's because there's 60 hertz noise being coupled in here, which causes modulation of the frequency. But this is the sort of thing you'll be doing when you do your touch sensor. If I get close to it but not actually touching it, the frequency drops, but not as dramatically, down to 330 kilohertz from about, I guess it's about 600 now. And when I actually touch it, get it way down. So the combination of both the display here and measurement capabilities can be very useful. And it's one of the advantages of a digital oscilloscope. Another one is, let's stop this and say, hey, you know, I'd like to look at that thing do some computations with it that the oscilloscope doesn't do for me automatically, I can export that data. Go up here to the export button, and now I can say, hey, I want to save this oscilloscope data, and I have the time, I have what's on channel 1. My notes here are irrelevant, so I can eliminate them. There's also a bunch of metadata here that says power supply is on, that's got a 5-volt power supply, the negative supply is off. I'm looking at channel 1, what the range is, what the offset is, what sort of triggering I'm doing. So all the controls there that I had are visible. I do not have to sit down and type in all the parameter settings that I made. So I've got the headers here as a comment. That means it's got this little pound sign in front of it, so that I can just read this data file in with something like GNU plot. It's just going to be 2 columns of data with a bunch of metadata at the front here, and I can say that this is the hysteresis oscillator untouched. So I've got some notes here that tell me about the conditions that the software can't know about because they're out there in the real world, not settings of the instrument. I can give it that information and include that as metadata in my data file also. And then just on my head here is a save button. I can save this thing. It uses the usual save dialog boxes for whatever operating system you're in, Linux, Mac OS, or Windows. Okay, when you're doing saves, there's another way to save just a picture of the thing, basically a screenshot. That's pretty nearly useless. It's very difficult to take a screenshot and get the data back out of it. It's very easy, if you've got the data, to produce images. And you can zoom in, you can select just as part of the data, all kinds of things you can do if you've got the data. Not much you can do if you've just got the image. So I don't want anybody turning in images, screenshots to me. I want you to collect data, save data that you can analyze, you can plot with GNU plot, you can do all kinds of things with. So always, always export your data, not just an image. Okay, I'm not going to bother saving this because I don't really need this data for anything, but know that that's there. And you can see I've only touched a few of the controls on this oscilloscope. It's got a lot that it can do, but what I've just shown you will get you through most of at least the first half of the course. We'll look at some of the other instruments on the Analog Discovery 2 in the second half of the course.